Text section is resonance. Resonance means a special case of forced harmonic motion. Special case of forced harmonic motion means we get two frequencies. This P is the external frequency or the frequency of the applied force, and omega 0 is the natural frequency. When matching of frequency, we studied this resonance in plus 2. The matching of frequency is called a resonance. Matching of which frequency? The natural frequency omega 0 and the external frequency P. What happens? This matching of frequency occurs. When matching of frequency occurs, body oscillates with maximum amplitude. Okay, so the result is maximum amplitude. Then this condition is called a resonance. So we are familiar about resonance. Resonance means matching of frequency. Matching of frequency means external frequency becomes equal to the natural frequency, and at this particular frequency alone body oscillate with maximum amplitude. Okay, so in forced harmonic motion we know the condition for or we know the expression for amplitude. What is the expression for amplitude? Amplitude is equal to f0 by root of omega 0 square minus p square the whole square plus 4k square p square. This is the expression for amplitude. If these two frequencies becomes equal, that is external frequency become equal to the natural frequency, body oscillate with maximum amplitude. That means this value should possess maximum value. But we know f0. What is f0? F0 is equal to f0 by m. This is a constant. Okay. So there is no change for this f0. Then this denominator should possess minimum value. That is the condition for maximum amplitude. Here, what's the minimum value of f quantity? Minimum value means it is equal to 0. If we take this equal to 0, then what's the value of amplitude? A is equal to f0 by 0. What is f0 by 0? It is infinity. So this condition is wrong. That means if denominator is equal to 0, the maximum amplitude or the value of amplitude is at infinity. But here the maximum amplitude means it has a particular value. Maximum amplitude means what's the meaning of maximum amplitude? This is x equal to 0. This is x equal to a. Okay, so this distance is called the maximum amplitude. If you oscillate an oscillating body, if you apply an external periodic force, this oscillates under the influence of this external periodic force. That means with the help of that external force, body oscillates with maximum amplitude. So this A has a particular value is there. It is not infinity. So this condition is wrong. So we can take denominator should possess minimum value means the condition for minimum value is d by dp, because here the variable is p, external frequency. D by dp of this function omega 0 square minus p square the whole square plus 4k square p square. This value, this is the smallest value which can be taken out from this function. Okay, this smallest value equal to 0. This is the condition for minimum value. Okay, here one root is there, but here we write this term as d by dp of omega 0 square minus p square the whole square plus 4k square p square. Why we neglect that root? Here we consider the minimum value of a function. If we take this, if we squaring that function, or if we take cube root, or if we take a cube of that function, from that if we find out the minimum value is always same. Okay, minimum value of the function, it is always same. Here we find out the minimum value of this function. That's why we neglect that square root. Okay, so d by dp of this variable or this function which is equal to 0, this is the minimum value of the denominator, and at this condition body oscillate with maximum amplitude. Okay, so here we can find out d by dp of, that means differentiate this denominator. So we get 2 into omega 0 square minus p square into minus 2p plus 4k square into 2p, that is equal to 0. From this we can take 4p as the constant. So we get omega 0 square 4p, then one minus is there, so minus omega 0 square plus p square plus, if you take 4p, then 2k square is equal to 0. Okay, so product of two terms, 4p into this term is equal to 0. 4p has value, so it is not equal to 0. Therefore we can write minus omega 0 square plus p square plus 2k square equal to 0. From this we can write p square is equal to omega 0 square minus 2k square, or p is equal to root of omega 0 square minus 2k square. So what's the importance of this p? At this particular frequency alone, body oscillate with maximum amplitude. So this is the condition for frequency at which body oscillate with maximum amplitude, and this frequency is called a resonant frequency. Okay, so here a resonance means matching of frequency. Two frequencies become equal, that is external frequency become equal to the natural frequency. So it is a special case of forced harmonic motion. Under this condition, body oscillate with maximum amplitude. We are familiar about the expression for amplitude in forced harmonic motion. It is f0 by this term. Here, if amplitude is maximum, either this numerator should possess maximum value or the denominator should possess minimum value. Here numerator is a constant, so the denominator should possess minimum value. What's the minimum value of denominator? If we directly take it as equal to 0, amplitude is equal to infinity. So this condition is wrong. Therefore, we take the minimum value of this function is d by dp of that function, which is equal to 0. That is the condition for minimum value. This is minimum value. When this minimum value equal to 0, it is equal to 0 is the condition for minimum value. Okay, when it is equal to 0, body oscillate with maximum amplitude. From this condition, we differentiate this equation and we get p is equal to root of omega 0 square minus 2k square. What's the meaning of this p? At this particular frequency, body oscillate with maximum amplitude. Okay, this frequency is called resonant frequency. Resonant frequency. So what's the importance of this resonant frequency? For an example, if we want to tune a radio station with frequency 98.3, it is an FM station, 98.3 frequency value. Okay, so 98.3 is the natural frequency of that radio station. If we want to tune this radio station in our mobile, we set the frequency values from 98.1, 98.2, 98.3, then 98.4, 98.5. This is the different frequency values. We are trying to get that radio station. Okay, when 98.3, we can hear music along with noise. That is music plus noise. Then when 98.2, we get more music plus less noise. Okay. Then at 98.3, what's the importance of this 98.3? 98.3 is the frequency, radio frequency of that FM station. So at 98.3, we get music alone. That means good quality of music we can hear. Then when it becomes 98.4, again music plus noise. Music plus noise. Then 98.5, noise increases, music decreases. Again 98.6, music decreases, noise increases. So at this particular frequency alone, body oscillate with maximum amplitude. As a result, at this particular frequency alone, we can hear the clear sound. Okay. In the case of TV signals also, when the signal frequency becomes equal to the receiver frequency, we get that channel. Okay, so this is the importance of this resonant frequency. Along at this particular frequency alone, 98.3, if it is the radio frequency of that FM station, at this particular frequency alone, we get the clear sound. When the frequency value is less than or greater than this particular frequency, we get music along with noise. If frequency value decreases, the noise increases, noise value increases. If the frequency value increases, again noise value increases. So at this particular frequency alone, we get crystal clear sound. Okay, this is the importance of this resonant frequency. So if we draw the graph of this resonance, we can take frequency value along the x-axis and amplitude along the y-axis. Okay, if we draw a graph, the shape of the graph is like this. So at this particular frequency, this value represents maximum amplitude, amplitude maximum. Okay, and maximum value of the particular frequency at which this maximum amplitude occurs, this is called a resonant frequency. So here we can represent it as PR. PR is the resonant frequency. If the frequency value is less than the resonant frequency, that is if it is 98.3, here the 98.2, 98.1, 98, etc. So this region, this is frequency value less than PR. At this region, amplitude is found to be decreasing. Amplitude is found to be decreasing means in the case of radio station, noise is increasing. Okay, when the frequency value is greater than this resonant frequency, that is this region, greater than resonant frequency, what happens? Amplitude is also found to be decreasing. Okay, so at this particular frequency alone, body oscillate with maximum amplitude on either side of this resonant frequency. On either side of this resonant frequency. Okay, on either side of this resonant frequency, amplitude is found to be decreasing. The rate of decrease, here amplitude is decreasing in a sequential order. The rate of decreasing amplitude, that term is called sharpness of resonance. Sharpness of resonance. Okay, so this is called a sharpness of resonance. On either side of resonant frequency, amplitude is found to be decreasing, and that rate of decrease of amplitude on either side of this resonant frequency is called sharpness of resonance. Then we have to explain some examples of resonance. Examples of resonance. First one is a radio or TV channel tuning. We just explained this case just now. That is when the radio signal frequency, it is the natural frequency of that radio station. When that frequency becomes equal to the receiver frequency of our device, we can hear the music or we get the TV channel. That is the one example of resonance. Then the second one is a resonance column experiment. Resonance column experiment. So in resonance column experiment, a liquid column is there. This liquid column vibrates and the frequency of vibration of this liquid column becomes equal to the frequency of vibration of the tuning fork placed. Good quality sound can be heard. Okay, that is the resonance column experiment. Then one more experiment is there, that is sonometer experiment. In sonometer experiment, a metal string is there. So we place a paper piece. Then a tuning fork, vibrating tuning fork is placed near to that string. When the frequency of vibration of this string becomes equal to the frequency of vibration of this tuning fork, matching of frequency occurs, this paper piece fly away. So these are some examples of this resonance. Okay.